Hello and welcome to another Advent of Code video. In this one we're going to be covering day 10, which, oh my goodness, day 10 was so much more code than any of the other days. I'm actually not going to resolve the problems here, so we're going to do a little bit different. I'm going to show a bunch of hints and stuff, and then walk you through how I solved the problem, and also tell you some other ways that you could have approached it, where, like, I did things less efficient than they could be. But anyway, let's jump into it. Okay, so the problem for today is a bunch of tiles, and the tiles have, the tiles are essentially puzzle pieces that have IDs on them. So if we look at, I'm going to open up my solution here, and this is for part 1. This is what these tiles kind of look like. They have the word tile, a tile ID, a colon, and then a map here. And this map has, you know, dots and octothorpes, and we'll deal with what those actually are later. But note that these kind of represent puzzle pieces in that they have markings on each of their edges that will end up matching up against other tiles, or they might not match at all if they're on an edge or a corner. And yeah, and the kind of frustrating thing about these puzzle pieces, or a thing that makes this problem hard, is these puzzle pieces can be rotated, or they can be entirely flipped. So it's kind of like a jigsaw puzzle, but you could solve it from the bottom, looking up at a ceiling instead of looking down from the top at the puzzle pieces. And so that makes this a lot more difficult. Given both flipping and rotating, that means that any of these puzzle pieces could have 8 different orientations, and being able to manipulate those 8 different orientations is kind of important for the puzzle. But that's kind of our input. For part 1, we are to figure out what the corners are, and I'll talk about a way to strategize that in a second, and then we're going to multiply their IDs together. Let's actually start with the parsing, and I'll show you my parsing here. But what I decided to do for this particular problem is to put everything into a tile class, and then use this tile class to solve the problem. And so my tile has essentially 2 members: the tile ID, which is going to be an integer, and the lines of the tiles. Now note, because we actually know a couple of things because of the rotation here. We know that all of the tiles are squares, and so that maybe simplifies the problem a little bit, or maybe gives you something to think about. Another thing that I noticed from our puzzle input, both of the puzzle inputs, is the output is a square. So there's going to be a squared number of tiles here. In the sample input, it's 3 by 3. In the actual input, it's 12 by 12. But I used those facts to simplify the problem a little bit for me. As for the actual parsing part, it's not too difficult. You'll just split by new line, since that's what separates the sample input down here, these blank lines here. And you'll also, split the lines out, grab the tile ID from the first line, and then use the rest of the lines for the body here. One thing to note, there's actually a bug in the sample input in that there's an extra new line at the end. So I made sure to strip out that extra new line. I spent a long time trying to figure out why I was getting a weird bug here, but make sure to strip out that extra new line so that you're not, butting up against that. But now I want to show you kind of a visualization, how I thought about this problem a little bit, at least for part 1. Part 1 you can solve entirely without having to solve the actual puzzle, and you can use a little shortcut for that. So I've drawn a bit of a simplified version of this problem here, where we have 5 long markers on each of these sides here, and they're going to line up in particular ways. And you don't actually care how they align, so they could align forward or backward, and that's fine. Note here that I'm assuming that a flip operation is going to take any of these markers and just make it completely backwards. I actually don't think I draw any that are backwards. I mean, this one, no, that one's not backwards either. I should have drawn one that was backwards. Oh well, pretend I drew one that was backwards. So we're gonna actually treat each of the edges as separate strings and flip them back and forth. But if we try and line any of these up, so let's say, dot dot triple thing here. We know that these 2 line up there. We know that, I guess we can just pick a bunch of different colors. Oh. We know that these 2 line up. And what else do we know? Oh, dang it. I messed this up. There's supposed to be another octothorpe here. And we know that these ones line up. And this one might align to something else, but if we only have 3, we know this is an edge piece, so it doesn't have anything else there. And you can kind of use this same fact to solve any of the other ones. And this means that a corner will only have 2 that line up with other ones, and 2 that don't. And so you can use that fact to find the corners. Now, this would break down if there were any non-unique edges, but it happens to be that the sample input and the actual input don't have any, overlapping edges. So there's all of the matches will be unique, and there's no duplicates there. So that's fine. But say like this piece here had one match here, and maybe another match here. But no matches on these 2, you would know that it has to be a corner. Now, you don't know which corner it is, and it actually doesn't matter which corner it is, because we're going to be flipping and rotating the final puzzle anyway. But identifying the corner, for me, was really useful for figuring out part 2, and, well, you need to do it for part 1. So here's how I did it for part 1. That's part 2. So part 1, I actually had a simplified version of the tile. I found that this was not enough information to actually solve part 2, so I didn't move forward with this same data structure. But I basically had the forward edges, so compute all the edges by grabbing the first line and the last line to get the top and the bottom, and then the 2 columns to get the left and the right. I ended up realizing that reversing this string and reversing this string actually made me have the incorrect answer for part 2. But for part 1, it didn't matter. I just needed some version of those edges and some version of the reversed edges. And then I basically just took every tile and looped over every other tile, making sure to skip comparing myself, and figuring out how many edges did not match. And so I kept a set of the original edges and discarded an edge if I found a match in some other tile piece. And then I knew that if there were 2 edges left, so 2 that didn't match, I had found a corner, and so I appended my corners. And then finally at the end, I just multiplied all of the corners together. So I felt like part 1 was pretty easy to solve. I solved this one in a matter of minutes, but I spent many hours on the second part. But that's part 1. If we look at algorithmic efficiency here, this is n squared because we're looking at every tile compared to every other tile. You could probably do some smart sorting or something here to get this down to like n log n, but I didn't bother. You could also probably use the 2-sum trick that we did in day 1 actually, and solve it that way as well. But I don't know. I wasn't optimizing for algorithmic efficiency. I was optimizing for ease of readability and code. So that's why I approached it this way. But anyway, that's part 1. Part 2, as far as I know, there's probably some super clever solution where you don't actually have to solve the puzzle. But as far as I know, you have to solve the actual puzzle in order to solve the puzzle. Wait. You have to solve the jigsaw puzzle to solve the programming puzzle for part 2. And the way I thought about solving the puzzle for this one is to first identify our corner piece. And it doesn't matter which corner piece. I just picked the first one that I found. And I made sure to orient that corner piece in a way such that it was my top left piece. So that meant that like, this had to match with something and this had to match with something else. Dang it, why did you turn orange down here, silly piece? Anyway. So I made sure that I grabbed this piece and found it and oriented it such that it was in this position here. Then what I did is I solved each row one at a time. I knew which pieces were the right cardinality such that I could find how they lined up. And I knew that because I had oriented this piece properly, as long as I orient the next piece to match this one, I knew that it was oriented properly. And so then I solved down each row. So I, solved down this row here, and then I solved, this row here. Once I had solved one row, I knew that I could match up the piece that starts the row by looking at the bottom marker on any of the pieces. I also wrote some functions that make it really easy to find the edges and find their reversed edges such that I know when things match up. I'm going to walk you through each of those functions that I wrote for part 2 on my special tile class. So again, we construct our tile based on the tile ID and the lines. So the lines is just a list of strings. Well, in this case, I used a tuple because I wanted to make sure things were immutable and I didn't actually break stuff. And so the first thing that I wanted to compute was the actual edges of a piece. And the way I did the edges is I made sure to keep them in the same order so that I could think about the problem easier. And the way I did my ordering was top, right, bottom, left. You could pick whatever ordering you want. I just happened to do it this way so that it was easier to think about for me. And this meant if I was looking for a particular edge piece, like if I was looking for the corner and I wanted two things to match up, I should make sure that the right and the bottom match up, and that would mean that I found a top left corner. Or I could orient it such that, you know, right and bottom are the ones that match. But for the actual edges, it's just the top line and bottom line. That'll get you top and bottom. And then for right and left, I joined the string portion, the single character of the string. And this is the right edge, and this is the left edge. Now note, I don't actually reverse any of them here, so I'm just treating them at face value. This works nicely if you need to stack things on top of each other without having to flip them. Now I also did the flipped edges here. I really only use this to match up the two pieces to figure out like what cardinality a piece had. But you know, when you flip something over, its edges are just going to be reversed. And so this is how I did my backwards edges. We eventually need to figure out the inner parts of our pieces here. So even though we have, you know, external edges here, we actually slice the edges off when we eventually fill in the puzzle to try and find our sea monsters. So I have a little function that does this. Next, I have two functions that I use to rotate and flip the piece. Rotation, I spent a long time trying to figure this out, and I'm going to kind of gloss over this a little bit, but I would suggest writing out a puzzle piece that's simplified. And so the puzzle piece that I did looked like, you know, 1, 2, 3, 4, 5, 6. Now, granted, I'm using characters that are actually illegal in the puzzle, but writing out a puzzle piece like this and then rotating it made this a lot easier to visualize. I then played with list comprehensions to try and get the actual, you know, rotated piece out. But like, if this were rotated to the right once, we would expect to see 7, 4, 1, 8, 5, 2, and 9, 6, 3 as our three rows. I actually think rotating to the left is easier, but I don't know. For me, I rotated right just because that was how I was thinking about the puzzle. Now, flipping is a lot easier. I decided to flip over the x-axis. You could also rotate over the y-axis where you just swap all of the rows for each other. But rotating around the y-axis is just reversing each of the strings. So you can imagine, you know, you take something like this and you flip it, and so now all of the rows are backwards. And so that's how I implemented a flip here. Now I kind of brute forced how to line all the pieces up, and so I wrote a function which yielded all possible combinations of a particular piece. And so it starts by yielding itself, then rotating 3 times and yielding each of those, then flipping it and then yielding that, and then rotating the flipped thing 3 times. So I end up with 1 plus 3 is 4, plus 1 is 5, plus 3 is 8. And so these are kind of my 8 different combinations. And I use this to kind of, you know, orient a piece properly relative to another one to make sure things line up. And finally, I had a representation. This made things a lot easier to, you know, see the actual pieces and print them nicely when I was debugging. This isn't actually necessary for the actual problem. Let me show you what that kind of looks like. Babby part2.py. When we construct a tile, break a point and pass. And if we PyTest this, you can see that this is kind of what my tile class looks like, this piece here. So tile ID, and then, you know, my piece laid out nicely. This actually doesn't properly make a tuple. Like, these should have commas on the end here. But I found that the commas actually kept throwing me off because I would see them as periods. So this helped me visualize this problem a lot better. All right, let's actually jump into how I solved this. So first, I did my parsing. Next, what I did is I looped over all of the pieces and all of the other pieces, very similar to part 1. And I figured out how pieces connect to each other. I actually didn't end up using this connections, did I? No. This would have actually made the problem more efficient, but I didn't end up using this. So ignore connections for this, but I keep track of a by connection. This is basically to figure out the cardinality of each of the pieces. And so I count how many edges have things matched up, and at the end I add them to sets that are just those tile IDs. And so this allows me to figure out whether a piece is an edge, a corner, or a middle piece. And we use that to try and figure out which pieces match up to each other. The next thing that I did is I found the corner, and I did that with this first corner function. This first corner function actually looks very similar to that function down there, and if I were to clean this code up, I would probably combine the first corner function with that actual parsing here. It adds some runtime overhead, but I don't know, I felt that it was easier for me to reason about the problem by splitting those two pieces up. And again, this is very similar, just like orient the two pieces. One thing that I did here that's a little bit different is I noted which edges were matched. So in my particular case, like if the edges that I matched were not 1, 2, so if I wasn't oriented in a way where, actually, let me do that this way for you. So these are, okay, top and left are the corners that are not matched, and then right and bottom are the ones that are matched. And this was so I could orient my puzzle piece such that I knew it was the top left corner and it was oriented in the right place. And to do that, again, I'm just rotating this using that rotate function I had here and adjusting by matched edges. This way, when I return from this first corner function, I make sure that my tile is oriented properly. And I'll use that to solve the rest of the puzzle. Okay, so we've grabbed that corner. Then I'm just going to loop over each row. The way that I'm doing my continuation here, if we go back to this drawing here, is I know what the previous bottom is. And so for the top left corner, I actually cheat a little bit and, grab whatever marker it has here. So let's say it had ... or octothorpe, dot. I know that this is the marker that I'm looking for, and so I can find my puzzle piece again. Even though I already know what it is, this just made it easier to think about finding each row at a time. And so I set my previous bottom to the corner.edges.top. That way I make sure that I'm matching the top edge with my imaginary bottom that's outside of the map. And again, this is my assumption that the puzzle is a square. I get the square root of the number of tiles, and I do a loop over that value. So I'm going to build up n rows where n is the width and height of the puzzle. Next, what I do is I try and find that first piece again. So for the actual corner, we already know what it is, but I re-find it here. So this is a bunch of extra work as well. And we know what cardinality that piece is supposed to be based on whether we're looking at the first row or the last row. So if we're looking at the first or last row, the first piece we're going to find should be a corner piece. Otherwise, it's going to be an edge piece. And so then what I do is I loop over everything that's of that right cardinality, and I try and see if the previous bottom is in either of its edges, either its forward or backward edges. Then I reorient the tile. So I do this, I loop through each tile until it's oriented in the right position such that its top matches the bottom. So this is, again, my rotating and flipping to get it in the right spot. And once I've found that, I put it into the row and I discard it from my cardinality set. So I make sure that I don't duplicate that tile anywhere else. And so this code here is just to find the first piece. After that, we find the rest of the pieces, and the rest of the pieces is pretty easy. We just loop through one to size. That way we find one piece at a time. And in this case, we're no longer trying to match the bottom of the previous piece. We're now trying to match the right and the left. And so we do, again, that same loop as I did before, but in this case, we're trying to match the right of the last item in the row with the left of the candidate tile that we're looking at. And so I loop over all of those, and again, I append it to the row, and I discard it from my set. Finally, once we've built up an entire row, we can add that to our set of rows, and we also reset previous bottom to the first item in the row that we just processed. But after we've done that, we've built up all of our rows. So this is, when the puzzle has been solved at this point. And once we've solved the puzzle, we need to take all of the inner bits of each of the tiles and remove all the edges around it. And so that's what I do here. This list comprehension is kind of hard to explain, but I did just some trial and error to get to the right part here. But note, we're looking at the inner parts here, and we're joining each line of those inner parts. Again, the inner parts are this, all of these lines in here, but ignoring all of the edges. And I actually reuse my tile here to represent the entire board. This makes it a lot easier for me to rotate and flip my entire board later. But I build this up. I give it a dummy ID. The ID doesn't actually matter here. And then finally, we loop over all of the possible grids. And so this will give us every orientation of all of those inner parts. And I try and match the 3-lined dragon inside, or sea monster, or whatever it was. I try and match it in each of those combinations. Now, they gave us a hint in the puzzle that the dragon will only match in one orientation of the puzzle, and so we know that we can just kind of skip over this if the count is non-zero, and as soon as we found one that matched, we know we're done. Now, I used regular expressions for this, and my regular expressions actually have an interesting trick here. I just copy these out of the input, but you'll note that the first dragon, I make sure to use this forward look ahead here. And this allows me to match overlapping matches here. And I'm actually replacing all of the spaces with dots, since the input said that we're looking for our dragon or our sea monster, but any of the places around it could be any character. They could be another octothorpe, or they could be a dot. And I'm using dot here as a wild card to match either of those characters, so I don't actually care about it. But I didn't want to make an error transposing this, so I'm replacing spaces with dots, and that's what's going on here. But the reason that I use a look ahead here is they might overlap. So you might have a match at this position, and then have another match at the position right after it, or the position right after it. And if you didn't do this, the regex engine would find this match, and then it would start searching directly after it, and you would never get overlapping matches here. So we need to make sure that we have overlapping matches so that we can find the right dragon there. But once we find one match, way down here, there's a lot of code for this. Once we find one match, we then look at the line after it to see if the second line matches at exactly the same position. So that's what this bit does here. And then we look at the line after that to see if it also matches there. And if we find all three of those matching, then we can increment our count. Finally, once we have found some orientation of our total grid that has a non-zero count, we can sum up all of the octothorpes on that. This will actually be the same value for any of the grid orientations. And then we can subtract out each of the dragons. I assumed here that the dragons didn't overlap, and it ended up being correct. And there are 15 octothorpes in each dragon, so I subtract that out of the full amount, and that's how we get our solution. Whew, okay, so a lot of code to solve this one, a lot of moving parts. This one was by far one of the most involved problems that we've seen for Advent of Code. But I finally got there in the end. It took me almost 6 hours to solve this problem. Then again, I was super tired for the first 3, so I wasn't really thinking super straight. But anyway, that is how I solved this problem. Hopefully this is helpful in some way. This problem is very, very complicated, so don't worry about spending a lot of time on it. But anyway, I'll see you again for day 21. Bye!